Hello, I'm Maria. I introduced myself in the previous lecture about an introduction to quantum circuits, and today I'm going to be giving the next lecture about Hamiltonians and how quantum systems evolve over time. I'll also be talking a bit about complexity and how we define the complexity of quantum algorithms. So you can see from here that I've called this lecture Time to Evolve, Hamiltonians and Time Evolution of Quantum Systems. So just to summarize some of the things that we'll be going through today, we'll talk about the Schrödinger equation and how this relates to unitarity and understanding how subsystems evolve over time and how we can start to compute things about how quantum systems evolve over time, for which we'll need to understand exponentials and commutativity. And we'll also talk about some quantum algorithms that are particularly useful and become involved when we're thinking about simulation. And we'll also talk about the complexity classes and what kind of notation we use for different complexity classes. So let's start with the Schrödinger equation. So the Schrödinger equation is a really important equation in quantum mechanics because it tells us how quantum systems evolve. So let's write it down. It's a differential equation. So here we have the imaginary number I, which we're familiar with. H bar is Planck's constant. And we often kind of make the simplification that we treat Planck's constant as equal to 1, which is useful to simplify our equations so that we've not got the H bar hanging around everywhere. So sometimes that will disappear, and that's why. Then we have the differential of the ket representing the quantum system that we're interested in, psi, with respect to time. And this is equal to this operator, which we've denoted by H. So I'll just put a hat to make it clear it's an operator, acting on this quantum system that we're interested in, represented by psi. So we're going to be very interested in this operator here, and just to make it clear, even though we use the letter H, this operator is not the Hadamard gate. It is actually it means something different, and I will use the gold pen because this is a very important part of today's lecture and quantum simulation in general. And this operator is called the Hamiltonian. So we have this operator that comes into this equation, which describes how a quantum system evolves over time. And so if we know what the Hamiltonian is for a system, then we know all of the dynamics for how that system will then evolve. So what we really want to do with quantum algorithms that are useful for simulating the dynamics of quantum systems is to be able to simulate the Hamiltonian of that system. So we'll be focusing a lot on how to represent this Hamiltonian and how we can then simulate that with quantum computers. So just some important properties of the Hamiltonian are that it is Hermitian. So we have mentioned before that it's if an operator is Hermitian, then it's equal to the adjoint, which is the transpose and complex conjugate of the operator. And we can also write out because it's a Hermitian operator, we can write it out in its diagonal form. So when we write the operator as a matrix, a diagonal, we can diagonalize that matrix, in which case it will only have diagonal elements, and the eigenvalues of the matrix, the eigenvalues of the operator will be those elements. So let's say we have, let's call these eigenvalues E1, E2, up to En. Then we can write our Hamiltonian in terms of Dirac notation. We can write it as a sum over, let's refer to the basis that we're working in as K. So this K will be 0 and 1 if we've just got a qubit, but it will be more if we've got more basis states. And then we can write it as, we can write the Hamiltonian in this way. So this is representing the matrix, the diagonal matrix. And then the interesting things to point out about the Hamiltonian is that, let's use purple, these eigenvalues of the Hamiltonian, they, for physical systems, they represent energy. So we call them the, they tell us the energy of the system. And then we have the eigenstates of the eigenstates of the Hamiltonian are energy eigenstates. And so the energy eigenstates represent the different levels of energy that the system can have. And the eigenvalues tell us how much energy there is in those different states. And so if we have a Hamiltonian for some system which has a range of energies, then the lowest possible energy is what we call the ground state energy. So let's say the lowest is the ground state energy. And the the eigenstate corresponding to the eigenvalue with the ground state energy is the ground is the energy eigenstate of the ground state. I mean, the energy eigenstate corresponding to the eigenvalue with the lowest value is the ground state. So those are some important aspects of the Hamiltonian. And we can then start to think about, so we'll go on to a new slide. So just as an example, a Hamiltonian could be h bar omega x. So this is the x gate, and this omega is just a number. So we just have these constants multiplied by x, which is our familiar x gate that we've worked with before. Then what will we find if we look for the eigenstates and eigenvalues of a system with this Hamiltonian? Because that's how we can work out what the ground state is, and which is the lowest energy state, and what the ground state energy is. So the eigenstates will be the same as they are for the x operator, because we've just multiplied it by constant. So the eigenstates will be plus and minus. And if you remember, this is the matrix for the x gate, so you can check that. And plus was 1 over root 2, 0 plus 1, and minus is 1 over root 2, 0 minus 1. And then the corresponding eigenvalues, the ones for the x gate are plus 1 for plus and minus 1 for minus. And so we just can multiply them by this constant prefactor. So we have plus h bar omega and minus h bar omega. So then we know that the lowest value eigenstate is minus h bar omega. So this is our ground state energy. And we have that our ground state is psi. It is a minus. So that's just an example of how you can start working things out about a system given its Hamiltonian. So to work out how to work with more complicated Hamiltonians, we're going to need to be able to introduce some tools, some mathematical tools to work with them. So one thing that we're going to need to be able to do is work out the exponential of a matrix. And this will become important because when we want to solve the Schrödinger equation, to get a general form for what this psi looks like and how it evolves over time, in order to solve that, we're going to need exponentials, and we need to understand what taking the exponential of a matrix means. So let's have a look at that now. Exponential of a matrix. So there are different kind of functions that you can do on a matrix, and the general rule with these functions is that if you have your matrix diagonalized, then the function on the matrix overall is the same as doing the function individually on each of the diagonal elements. So let's write this out, that if you have your matrix, let's call it M, and let's say we have a sum over, let's call them little m. Let's go with K again, because we used that before. K, and then then you've got your eigenvalues, and so this is the matrix written in its diagonal form, in the basis in which it is diagonal. And then this corresponds, doing some function on this matrix is the same as doing that function on the individual eigenvalues if the matrix is diagonal. So now that we have the this rule, we can apply it to exponentials. So let's say we want to work out the exponential of m. That's going to be the sum of the exponentials of the eigenvalues when it's written in the diagonal basis. And we can see this as a matrix. So if m is E1 to E, so it goes up to big N, then the exponential of m is going to be the exponential of each of the elements of n. So I probably shouldn't have used E as my letter for the eigenvalues, because now it mixes up with the exponential E, but I'll just make that clear by writing these out properly. Exponential of E1, exponential of En with zeros. So that's how we can take the exponential of a matrix. So just as an example, if our matrix was the Z operator, which is 1, 0, 0, minus 1, it's already diagonal in the computational basis, so it's a nice one to look at. Then the exponential of, let's say we have some parameter theta times Z, and we want to look at the exponential of this, then that's going to be the exponential of theta times 1 and theta times minus 1, which is, yeah, the exponential of theta, exponential of minus theta, 0, 0. So that's how we can take the exponential of a matrix. And with that in mind, let's think about how to solve the Schrödinger equation. So the solution to the equation to work out how this state evolves over time, we can write like this. So we have this state that's evolved over time, and we could write it as the exponential of I times the Hamiltonian operator times time over h bar. And then we have the psi at time 0, which is the initial time that our state started in. And we want to check if this is a solution to the Schrödinger equation. So let's substitute it in. So we have the Schrödinger equation is I h bar psi d psi by dt equals h psi. So let's check if this is true for psi of t. I h bar d by dt of psi of t is IH bar d by dt exponential IH t over h bar psi of 0 times 0. And what we can do with when you take the function of the h operator, we can do the differentiation by bringing it out of the exponential, and then we are left with this. And now you can see that I think I have missed a minus sign. So, and we add that back in, then we have a negative sign here, and you can see the minus I and the I and the h bar over h bar cancel out, and we just have h, and then that's all multiplied by psi of t, and so we satisfy the Schrödinger equation as we expected, which is great because now we have a solution for the Schrödinger equation. So what if we wanted to know how the state evolves from one time to another time rather than from 0 to t? Well, then we can consider the it doesn't have to be 0 to t. It can be, we can call it t1 and t2 in the same way that we worked out that it works for time 0 to time t. So we can also write this solution as psi t2, so some general later time is exponential of minus I h t over h bar of t1, of t2, and there we have multiplied by, or acting on psi t1. So then, sorry, this, I actually missed something out here. Whereas before we had t, because we had t was the time interval from 0 to t. Now we want the time interval between t1 and t2. So what we actually want is t2 minus t1. So we put that in. And we find that this is the general solution for two different times, and how it evolves from t1 to t2. So what we can do now is this part, we can just write that as a quantum gate in terms of t1 and t2. And this quantum gate is a unitary gate. So so we can actually check that it is unitary, and we will do that in a minute. But what that actually means is that we can see that you can evolve from psi at time 1 to psi at time 2 by applying a unitary gate. So what the unitary gates that we've been looking at before allow us to do is they kind of jump the state from, they change our quantum system from one state to another state in these jumps. And what we're doing now is looking at how that state evolves over a kind of continuum of times. So this T1 and T2, that gap can be changed, made bigger and smaller. And so that allows us to evolve the state, to look at how the state evolves kind of continuously, whereas before we were looking at, when we were just looking at it in terms of applying these unitary gates, we were looking at it in terms of these discrete jumps, where each gate we apply causes a discrete jump of the quantum state to a different state. But we can see from, and we'll show that every unitary gate actually has a Hermitian operator, such every unitary gate can be written in this form. And so we have this kind of one-to-one correspondence between the unitary gates and the Hamiltonians that describe the quantum system over a kind of over a continuum of times. So the two ways of looking at how the system evolves through a series of unitary gates, or by solving the Schrödinger equation between two times, become the same in this way. So to make sure of that, let's check that the unitary gate really is unitary. So let's give a title: Checking Unitarity. So to check that the gate is unitary, let's copy, paste. Okay, now we'll move it over here. Okay, so let's check if this is unitary. So this is u, and we want to do u adjoint times u, which is exponential of all of this in here. And we want the adjoint of that. Right, and what we can see is that when we take the adjoint of the function of the Hamiltonian, we can bring that inside we can change the minus to a plus I when we take the conjugate, and then the h becomes a h adjoint. And then the other thing we can notice is that the h joint, because it's Hermitian, this is equal to h, and then we'll see that the plus I and minus I will mean, well, they will turn out to mean that the total of this is an exponential of plus I h t2 minus t1 over h bar plus minus I h t2 minus t1 over h bar, which is exponential of 0, which is the identity matrix. So it is unitary, but there is a step here that I want to draw attention to, because there is something we need to be careful of when doing calculations like this, and it relates to commutativity. So let me do a kind of red line in the step that we need to be careful of, which is here. So I'm just going to write danger, because when we change exponentials of operators from products to sums, we need to be very careful. But it works out okay in this case. So that's what I'll explain now. Explain why the product of exponentials of operators isn't always the same as the exponential of the sum of those operators. We need to essentially the punchline is that the product of the exponentials is the exponential of the sum of the operators only if the operators commute. So let's look at what commutativity is. So if in general we have two operators A and B, then we say that A and B commute if AB equals BA. So that means that we can apply B to a state and then A, and that will give us the same result as applying A to that state and then B. And we'll also find if you just multiply the matrices, then they will be the same if we switch round the order that we multiply them if they commute. And so another way to write this is that AB minus BA equals 0. And a way that we denote AB minus BA is with these square brackets with A and B. And we call this the commutator of A and B. And another thing to point out, which we won't really be using much right now, but is good to know, is that there is also such a thing as anti-commuting. So if AB equals minus BA, then we have that AB plus BA is 0, and then we use these curly brackets to denote this expression. And so if that is 0, then we say that the operators anti-commute. So you might see that terminology used as well. But sticking to commutativity, let's have a look at what happens when we try and use exponentials when with operators that commute. So let's call this exponentials with commutativity. Okay, so we want to check what happens when we have an exponential of A and an exponential of B. And we've said that A and B commute, which means their commutator is 0. And there is an important property of matrices that commute that we're going to use here. And that is that if matrices commute, then they can be written, they can both be written diagonally, simultaneously diagonalizable. So just as an example, if we take like the X gate and Z gates, they are not simultaneously diagonalizable because the Z gate is diagonal in the computational basis, 0 and 1, whereas the X gate is diagonal in the plus minus basis. So they don't commute and they're not simultaneously diagonalizable. Whereas, yeah, any two matrices that can both be written diagonally in the same basis are simultaneously diagonalizable. So let's, so that means that we can write the matrix A as the, let's say the basis states are, let's say K. So we can write the matrix, the operator A in its diagonal form, and we can write the matrix or operator B in a diagonal form in the same basis. So what happens when we take exponentials here? We have exponential of A and exponential of b. And we saw from earlier that we can take the exponential of the functions of the eigenvalues and kind of, yeah, bring them in there. And now we have the neat outcome that we can just do, we can bring these exponentials together, and we can see if we bring these two together with our Dirac notation, the k and k will kind of come together to form an inner product with itself, which is equal to 1. And so we're just left with the basis states again. And so we have exponential of ak times the exponential of bk, which, because now we're just taking exponentials of numbers, we can use the rule that the exponentials of numbers, the product of exponentials of numbers is equal to the exponential of the sum of those numbers. And then we can kind of reverse our definition of taking the exponential of a function to say that this is equal to the exponential of a plus b, because a plus b will have eigenvalues which are the sum of the eigenvalues of the individual matrices. So we see that this trick of the exponentials, the product of the exponentials being the exponential of the sum, works if the matrices commute, but we can't use it if the matrices don't commute. So that's why we have to be careful. But if we go back to our solution for checking unitarity, we used the trick with H and H, which are the same matrix, so they clearly commute, because we have the commutator is 0. Right. So now we have been through this, then next we can think about how can we show that our next thing to check is that all of the unitary operators have a Hermitian operator, and so we really can map these unitary gates that take us from one state to the next. We can map them onto the time evolution of a system that is evolving according to some Hamiltonian, which is a Hermitian operator. So let's say unitary gates and Hamiltonians. So we want to be able to show that if we have a unitary gate in the form that for any unitary gate, so let's put any unitary, there is some Hermitian operator k such that we can express our unitary gate as the exponential of I times this unitary operator times this Hermitian operator. So that means we want to know if given some unitary gate does there exist a Hermitian operator for it? So we can rewrite this equation as k is minus I log u, and we can check if K is Hermitian. So let's write U in its diagonal form. So let's say we write it like this in its diagonal form. And again, we take our function in. And we know that the eigenvalues of a unitary matrix can always be expressed in the form e to the I phi for some parameter phi. So that you can check that using the have to basically always just have to have modulus 1. So that's why it's e to the I phi. And then we have minus I sum of k log, let's say e to the I phi k. And using rules of logarithms, that becomes I phi k. And then the i's cancel out. And what we're left with, we can see that this is Hermitian because it equals the same thing as an adjoint matrix. So we know that there is always a, that when we write U in this form, K will be a Hermitian operator. So we have this nice mapping between unitary evolution and so unitary gates and the time evolution brought about by Hamiltonians. Great, so the next thing to think about is how interestingly we can use Hamiltonians and unitary evolution to describe parts of a quantum system as well as the overall system. So up till now, we've been considering closed systems. So the Schrödinger equation tells you how a closed system will evolve over time. So that means a system that is not interacting with anything else. It's kind of isolated and evolving within its box or within its kind of isolated space. And now we're going to consider what happens if it's interacting with something else. So we call that an open system, where the system you're interested in is interacting with something. So let's call this evolution of subsystems. So let's imagine we have, we can consider the unitary evolution of a system as a whole. So let's have the system as a whole being inside this box. And now imagine there's two parts to this system. Let's say, for example, there's like a laser beam here. And it is being fired at an atom to affect some aspects to affect the quantum state of the atom. And so we've got two systems here, and we can describe them all together by a joint Hamiltonian to describe the system as a whole. So if we call that 1 and the atom 2, then we could write some Hamiltonian to describe both. But what we can also do is consider a Hamiltonian just for the atom. So this will be an approximation to the actual evolution of the atom, but we can get a good approximation by having some some approximate Hamiltonian of just the atom by itself. And this will correspond to a unitary gate. So we can approximately model the dynamics of this atom by a unitary gate. And this is important because if we can model it by unitary gates, then we can start to think about how to simulate it on a quantum computer, because everything there is unitary apart from measurements. So with that in mind, what we can consider is that this laser, for example, the person controlling it might want to vary the intensity of the laser. So let's say that that intensity is being varied, and that is kind of characterized by some parameter theta. So we have some, say an experimenter is changing the intensity of the laser from a small amount of small theta to a large theta. Then what we can do with our expression, our approximate expression for this Hamiltonian of the atom, can be a function of theta, so that we can incorporate the fact that it's interacting with the outside, interacting with this laser. We can incorporate that interaction approximately by having this parameter being part of the Hamiltonian that we're using for the atom. So this parameter can be varied over time as the system interacts with this laser, and we have like an experimenter changing the value of theta over time, and then we can see how that varies over time. So that's how we can model a subsystem still using Hamiltonians and approximating it using unitary evolution, even though it's not exactly unitary. So now that we've started discussing the evolution of subsystems, we're kind of getting close to the idea of what we're trying to do overall, which is to simulate Hamiltonians of systems. So we'll just discuss a bit about why simulating Hamiltonians is, why quantum computers might be particularly useful for simulating Hamiltonians. Great. So what we know is that simulating Hamiltonians classically is very inefficient. And I will just give a kind of brief argument for why this is the case. So we've seen that Hamiltonians are described by the Schrödinger equation. So I've just written it there again. And let's say, for example, we want the Hamiltonian of a particle moving in space. So in order to write down that Hamiltonian, we need to use something we call the position representation, or the position basis. And we define a the state of a particle as a function of its position using the inner product of the position basis ket with the state, and we denote this by psi as a function of x. And then when we have the Hamiltonian of, we have the, for a single particle, the way that the Schrödinger equation looks is that we have the partial differential of this psi with respect to t is equal to, then the Hamiltonian has two parts to it. We have a kinetic part and a potential part. So this is the kinetic part, which is where the kinetic energy of the particle would come out as the eigenvalue from operating on the state with the Hamiltonian operator. And then we have the potential energy part, where the potential energy would be the eigenvalue when you operate on the state with the operator. So this is our Hamiltonian in the position basis for some physical particles. Now, what is difficult here then? Because if you've done a bit of solving differential equations in a maths called these these equations, which are second order, because they've got the d2 by dx squared. But the problem is with the number of equations that we need to solve, because if we're just trying to simulate one qubit, so if we just have one qubit, then we're going to need to solve two equations, because the state is, so this x is like a continuous parameter of position over space. But if we're just thinking about a single qubit, then we're thinking about 2 points at which we want to compute this solution, which is when we've got the state being 0. We want to know how the 0 state evolves and how the 1 state evolves, and then we know how any linear combination of them evolves. And so then we need to solve 2 equations to know how the 0 state evolves and how the 1 state evolves. If we have 2 qubits representing our quantum state, well, then we need to know how all 4 computational basis states evolve, or any 4 basis states, but we're just using the computational ones for simplicity. Then we'd need 4 equations to solve, to characterize the evolution of 2 qubits. So what if we have n qubits? Well, then the number of computational basis states is going to be 2 to the n, and so we're going to need 2 to the n equations to solve. And so we can see that the number of equations we need to solve is increasing exponentially with the number of qubits, and that's why classical simulation is slow. And there are several approaches to this, to finding solutions to this. One is to use approximations for the Hamiltonian to simplify it and make the simulation more efficient. And the other option, which is the one we're interested in, is to use a quantum computer instead, which could help us simulate these more efficiently.